look at this problem itself, because this is a very important problem, and this comes in my exams in every semester. So let's understand this problem. This is when you add up all the partition coefficients that we studied into one. Let's look at it. A student uses a reactor to mimic the environment for a class demonstration. The sealed 1 liter. So we have a 1 liter reactor, a tank, a container. It's total 1 liter. And it is sealed, which means that you lock it up. There is nothing coming out of this reactor. It contains 500 ml water. If it has 500 ml water, it has 200 ml soil. And since it's 1 liter, you'll have air at the top. How much air? If it's 500, 200, or 700, you'll have 300 mils air. It's 1 liter total. And the soil has 1% organic carbon, so 1% FOC. The density of the soil is 2.1 gram per centimeter cube. Of course, 300 mil air. The temperature of the reactor is 25 Celsius, which is normal temperature. After adding, now he's adding to the reactor 100 microgram TCE. The student incubates the reactor until it reaches equilibrium between all phases, between the soil, water, and air. The Henry law constant for TCE, again, Henry law constant for all these organics, there's books. So this, you don't have to memorize. This is found in books. TCE Henry constant is 10.7 liter atmospheric per mole. We don't use this for our calculation. We have to make it unitless, dimensionless at 25 Celsius. TCE has a log KOW of 2.42. So log KOW of 2.42, assuming that there is no chemical or biological degradation, of course. Now we want to check the partition coefficient, the physical partition coefficient. We don't need any bacteria that will eat the TCE, and also we don't need any chemical reaction that will remove TCE. We need to check the partitions between soil to water to air, and air back to water, water to soil, like this. What is the aqueous phase concentration of TCE at equilibrium? He needs to know what is the organic. I mean, of course, if you let this sit at equilibrium, you'll have the soil at the bottom. You'll have the water here after equilibrium. And you'll have air. He said, at equilibrium, what is TCE concentration in the water? We call it C aqueous. Concentration of TCE in water. Aqueous mean water. Now, we know that this is the total organic that we put, 100 microgram. So we'll start doing a mass balance. Okay? Total mass of TCE added is equal mass of aqueous TCE in the water, mass of gaseous TCE in air, plus mass of sorbed TCE in soil. So we had to add up all the masses in air, in water, and soil. The mass of what? Mass of the organic, trichloroethylene. Total mass is 100 microgram. If you need to find out the mass of organics in aqueous solution in TCE, of TCE in water, remember from the previous one, we did define this parameter. The volume is in liter. So if you multiply volume times concentration, you will multiply liter times concentration, milligram per liter. So you'll have mass. So if you multiply volume times concentration, you will get mass. And that should be the same mass, microgram. Same thing we'll do for gas, volume air times C air, the volume of the air times the concentration of the chemical in the air. Same thing, and the last one, soil. Soil is a little bit different than treating air and aqueous. You multiply mass of the soil times what is the concentration of that organic that is sorbed into the soil. So what do we have to do? We have to convert, we need to find this C aqueous. We need to convert this to C aqueous using Henry law. And you need to convert this into also C aqueous using the KD and the fraction of the organic carbon law. Let's look for the mass of soil first. Of course, we know what is the volume of aqueous. We know what is the volume of air. Now we want to find out the mass of the soil. Remember, density is equal to what from fluid mechanics? Density is equal mass over volume. Okay, so mass is equal density times volume. So mass of the soil is equal density of soil times volume of soil. Volume soil, we know it, 200 milliliter from the example. Of course, you multiply this by the density, 2.1 gram per centimeter cube, and you convert milliliter to this, because 1 centimeter cube is equal to 1 milliliter. So milliliter goes with milliliter, you end up with centimeter cube divided by centimeter cube, and you'll end up with gram. So the mass is 420 gram. Okay, so we are done from this. 420 grams is the mass of the soil. Now, remember he gave you the KH, Henry constant for TCE, 10.7 liter atmospheric per mole. From the table that we just mentioned before for Henry law constant, if you divide this 10.7 liter atmospheric per mole by R, by the temperature in Kelvin. Remember he gave you the temperature in what? 25. You add up to it 273 to make it Kelvin. Okay? And this would give you 0.44. And this is KH. This is dimensionless KH. Okay. So we found KH 0.44. Remember KH? KH is equal the concentration of the organic in air divided by the concentration of the organic in what? In water or aqueous. So we have 0.44. We need to find C aqueous, so we could do it like this. C air is equal KH C aqueous or C water. Okay, C aqueous or C water. So we could substitute this C air, C aqueous times KH. Okay, because we need C aqueous, C aqueous, C aqueous. You could find C aqueous at the end. Now we're going to find C salt as a function of C aqueous. Okay, so now we finished this. Now let's go and find out the sediment. Remember the KD is equal KOC times FOC. And remember we have 1% organic carbon. So it's 1 over 100 is 0.01 FOC. Remember KOC was also from the equation that log KOC is equal 0.903 times log KOW 2.42 plus 0.094. You'll get 2.28, which means that KOC is 10 to the power 2.28. From this, you could find out, you have KOD, you could find out, you have KOC, you could find out KD. KD is equal what? 10 to the power 2.28 times what? FOC is 0.01, 1%. This is 1.9 centimeter cube per gram. And remember the KD? The KD is equal to what? The concentration of the organic in the solid phase over the concentration of the organic in water. Let's call it aqueous here, so we could have the same. So C aqueous is equal KD. C aqueous is equal, CS over KD. Oh, no. We need it as a function of C aqueous. So CS, the concentration of the solids, is equal KD times C aqueous, because we need to be a function of C aqueous. So we have the concentration of the organic in solids. We need to make it as a function of C aqueous. So now KD, we have it 1.9, and C aqueous should be there. So let's put it in the equation. 100 microgram, 500 milliliters, C aqueous, unknown, plus 300. This is for what? Water. This is for what? Air. Remember, 300 ml volume times 0.44 C aqueous, plus the mass of the soil is 420. Times what? Times, of course, this is, as we mentioned, is KD, times KD times C aqueous. KD is 1.9. Of course, you change centimeter cube to milliliters, so you could cancel up everything else at the end, times C aqueous. So now we have C aqueous, C aqueous, C aqueous. You could take it as a common factor and then add up everything else. You will end up with 0.07 microgram per milliliter. Okay, this is wrong here. So 0.07 microgram per milliliters. This is equivalent. This is the concentration in water. Remember, we mentioned before, milligram per liter is microgram. Let's change it to milligram per liter. This is 0.07 milliliter over liter. 1 liter is 1,000. Microgram to milligram. 1 milligram is 1,000. So it's 0.07 milligram per liter, which means it's 0.07 ppm. Let's multiply by 1,000. So 1, 2, 3, 70 part per billion. By mass, of course. So this is the concentration of the organic into the liquid. Now, of course, you'll have concentration. Remember the tank? It was like this. It will have soil, water, and air. So now we have the concentration of the organic into the water is 70 part per billion. Could you find out the concentration of the organic into the solids? Could you find out the concentration of the organic TCE in air? Okay, this is one way of rechanging the problem. Now we found the C aqueous. Let's say if I ask you what is the concentration of the organic in the solid phase? What is the concentration of the organic in the air phase? Okay? And that is simple to do, okay? Like, for example, if you want to find out the concentration of the organic in the solid phase, is KD. What's KD? We know KD. KD is 1.9 milliliter per gram. Times what? Times C aqueous. C aqueous is, let's see, it is times 0.07. If you convert microgram to milliliter, it is milligram per liter. Liter, milliliter. One is 1,000. So milliliter with milliliter and milliliter with liter. Now you convert, since we're talking about solids, we have to make it milligram per kilogram. So gram per kilogram. 1 kilogram is 1,000. So gram per gram, and 1,000 per 1,000, and you'll end up with milligram per kilogram. Now it is fine. So 0.07 times 1.9, it will be the concentration of the organic into the solid phase in milligram. Make sure you put unit per kilogram. If you want to find out the concentration of the organic into the water, into the water, we found it, aqueous, into the air, very simple. The concentration of the organic into the air phase is equal 0.44 times C aqueous. C aqueous was 0.07, or you could do it 70 part per billion if you want to. And that's going to give you in part per billion. So the concentration of the organic in the aqueous, in the air phase, is part per billion. Some question that came in the previous exam, that what is the percentage of the organic out of the total? What is, for example, let's see, what is the question here? Okay, let's say that we know the mass. We could find out the mass of the organic in soil, the mass of the organic in water, the mass of organic into the air. What is the percentage of the mass of TCE in the soil out of the whole compartment? What we do is we divide the mass of TCE divided by the mass of the whole things times 100. Okay, the mass in grams of TCE over the total mass, which is like 100. Mass total. Okay, in soil. Let's see, let's assume this is in soil. Okay, and you could find the percentage of distribution of the organic on these compartments, if you wish. We are done.